Hello everyone, today let's solve the problem number 133, clone graph, right? So what the question states here, we are given a reference to the node in a connected undirected graph. So this is an undirected graph. Let me come here. So we are given a reference to the node in a connected undirected graph where each node contains a unique value val. So where each node consists of the unique value val and the list of neighbors, nothing but neighbors. So this is each node consists of the unique value val. So this one is nothing but the val, and so it consists of the list of neighbors as well. So for one, the neighbors are 2 and 4, right? So we have been given adjacency list. Suppose we are considering this graph. So here adjacency list of 1 is 2 as well as 4, 2 comma 4. Adjacency list of 2 is in this case 3, 1 and 3, 1 and 3, right? So adjacency list of 3 is 2 as well as 4. Adjacency list of 4 is 1 and 3 again, right? So we have been given adjacency list. What we need to do here, basically our task is to deep clone the graph. We have to deep clone the graph starting from the given node and return the cloned reference. We have to return the cloned reference. Just keep this in mind. We cannot return the same graph. So we cannot return the same graph. We have to deep clone the graph. That is fine. Graph starting from the given node, and we have to return the clone reference. We have to return the clone reference. Just keep this in mind, right? So let's come to the this one here, first example. So they have clearly showed in the figure here. So here, see, you cannot return the same graph. We have the same graph with nodes. So if we try to return the same graph here, 1 2 4 3 we have here, right? Or 1 2 4 3 or 1 2 3 4. So here in this case we cannot return the same graph. They have clearly mentioned here. We have to return this one, right? Clone reference we have to return. So let's come to the second figure here. We have the original graph here, same thing. So here you can clearly see we have the same nodes, but they have given in the different color. This shows that this looks like a clone. The nodes are new. The nodes are completely new. That is the reason they have given in the different color, right? So the nodes are new. Graph looks the same. That's what they have given, right? So this is simple to understand. So this is what we need to return, basically, right? So our task is to deep clone the graph that is starting from the given node, and we have to return the clone reference. So that's what they have given here, right? So just give me a second here. Please just give me a second here. So let's come to the third graph here. So this one, this is properly cloned, no doubt, but the nodes were cloned, but the graph is messed up. Here you can clearly see the value, the neighbor of the one here is 2, the neighbor of the one here is 3. So this is messed up. That's what they have given here. So the neighbor for the 4 here is 3 as well as 1, right? Adjacency list if we consider here, it is 2 and 1. So this is messed up. They have given the graph is messed up. It doesn't have the same connections. So right, it doesn't have the same connections as this one. So this will be this doesn't work as well, right? So the first one, we cannot return the same graph, and also the nodes should have the same connections. That's what they are trying to say here. In this case, we have the new nodes and which have the same connections. That is the reason we need to return this one, right? So here adjacency list they have given. For 1 it is 2 comma 4, for 2 it is 1 comma 3, for 3 it is 2 comma 4, and for 4 it is 1 comma 3. In this case, output that we have got here is 2 comma 4 1 comma 3. Same thing, right? Same thing as the adjacency list. 2 comma 4 1 comma 3, 2 comma 4 and 1 comma 3. Here there are 4 nodes in the graph. First node val equals 1, neighbors are second node val equals 2, and fourth node. So that's what they have tried to say, the same thing here what I explained, right? So I'll just read out here. First node, we have the adjacency list here. This one we are considering, right? 2 and 4, right? So that's what same goes with this one. Second node 2 and 1, third node 3 and 2, fourth node 4 and 1, right? So the output that we need to get here is same thing as the adjacency list that they have given for the input, right? So same goes with example 2 and example 3 as well. We have only one node here in this case. So here we need to return the empty array within the array, right? So here explained, they have clearly explained here. So note that input contains only one empty list. The graph contains of only one node with val equals 1, right? So it does not have any neighbors. So in that case, we have to return this one. This is fine. So here in this case we have empty graph. Adjacency list means we have the empty graph that is given. So input empty array, so the output should be empty array as well. So explanation, they have clearly explained here, this is an empty graph, it does not have any nodes, right? So I hope the question is clear. I hope what we need to do is completely clear as well. Let me clean up this one. Just give me a second here. Yeah, now we are completely familiar with the question, right? So now we know what we need to do, and we have understood the question as well. First, what we'll be doing, let's discuss the approach first, followed by the edge cases one by one, and then finally write the code and discuss the complexities for the code that we have written. Initially, let's discuss the approach. So first thing that we need to note down here is we'll be making use of the DFS, right? DFS with the hash map. So just keep this in mind. We'll be making use of DFS with hash map, right? So this is fine. I have considered the same first example so that it will be easier to understand the approach that they've given in the question, right? The first example. So adjacency list, we have 2 4 1 3 2 4 1 3. This is fine. The same output that we need to get as the same this thing we need to get here as output, right? So we have already discussed this one. Let's move on with the step-by-step execution, right? Here we have 1 2 3 4. We have the original graph here. Original graph we have here. This is fine. So here this is a new clone. So basically this is a new clone right here. This is a new clone. The nodes are new here. In this case, the nodes are new here. In this case, the nodes are new. You can clearly see that is the reason we have been given here with a different color, right? So this is a new clone. The nodes are new and the graph looks same here. In this case, graph looks same. The nodes are new, but the graph looks same. Means connections are same. One is having the adjacency list 2 and 4. So basically, one is having 2 and 4, and 2 is having this one 1 comma 3, right? And 3 is having the adjacency list. So 2. So just give me a second. What happened to this one? So yeah, here 3 is having the adjacency list, this one 2 as well as 4, right? So I'll just give here 2 comma 4, and 4 is having the adjacency list here 1 comma 3, right? So I'll just give here 1 comma 3. Same goes with this one as well, as we are having the same node. So this is a new clone. The nodes are new, completely new, because we'll be going with a deep clone. Basically graph looks the same with the same connections, right? So this is what we need to do. Let's see this one step by step. Basically, first what we will do, we have the nodes 1 2 3 4, and the graph edges we have already considered this one, right? 2 4 1 3 2 4 1 3. This is fine for the node 1, node 2, node 3, and node 4. So next step what we'll do, we'll start cloning from node 1. So node 1, we will clone node 1 first, then its neighbor 2 and 4. So here when I say we will clone node 1, this means this one neighbors are adjacency list or the neighbors, this one 2 and 4, right? We will clone node 1 first, right? Node 1 we will clone, and then its neighbor 2 and 4. Basically for node 2 we have to clone its neighbor. 1 is already cloned here. So suppose 1 we have already cloned. 1 means we have cloned 2 and 4 for 1 here in this case. So just give me a second here. We have already cloned 2 and this one 4. So here we'll come to node 2 next. We have to clone 1 and 3. 1 is already cloned here. So in previous step itself 1 we have cloned, right? So 1 is already cloned here in this case, right? 1 is already cloned here. Then we will clone 3 in this case. Here we'll clone 3, right? Along with the 2. So next for node 3 we have to clone its neighbor, right? 2 is already cloned here in this case. So see here 2 is already cloned. This one I'm speaking of. 2 is already cloned here in this case. We will clone 4 here in this case. This is fine, right? Next let's move with the node 4 here in this case. Node 4, see for node 4 its neighbors are 1 and 3 which are already cloned. So 1 and 3 are already cloned. See here 1, this one is already cloned, and 3, this is also already cloned. So we have already cloned 1 and 3. We don't have to worry about that. So the final output would be 2 comma 4 1 comma 3 2 comma 4 and 1 comma 3, same as the adjacency list, right? So the output that we got here is 2 comma 4 1 comma 3 2 comma 4 1 comma 3, which is equivalent to the output that they have given for the example 1 in the question. So our approach works absolutely correct in this case. Now we are completely familiar with the approach, right? So we are completely familiar with the approach. As we are familiar with the approach, let's discuss the edge cases very quickly. Let's discuss the edge cases very quickly. The first edge case is for the empty graph here. So we have the empty graph, adjacency list is empty here in this case. So output will be empty array, right? So no nodes to clone at all here, right? Sorry, no nodes to clone at all here, right? So the output will be empty array. Let's come to the second example here. In this case, it is for the single node, no edges. So we don't have any edge here, single node we have, right? Single node, no edges. In this case, we have one node with no neighbors is cloned alone. So output will be same thing here. Array within the array. Empty array within the array. So this is fine. Let's move on with the third and the final edge case. Here, adjacency list is 2, 1. Right. So this is nothing but the cyclic graph. Right. So this is for the condition cyclic graph. So 1 is connected to 2 here and 2 to 1. So here 1 is connected to 2 and 2 is connected to 1 in this case, right? So both nodes are cloned without infinite loop, right? Using the visited map. So that is the reason basically we are making use of the hash map, right? So that is the reason we are making use of the hash map. 1 is connected to 2, 2 is connected to 1 here. So 1 is connected to 2, 2 is connected to 1. Both nodes are cloned without infinite loop using the visited map. So that is the reason we are making use of the hash map. You will come to know when we write the code this one even better, right? So that is the reason we are making use of hash map. So I said we'll be making use of, just give me a second here, we'll be making use of the DFS with hash map, right? This is the reason we'll be making use of hash map basically, right? So these are the edge cases that we need to keep in mind basically. The first edge case is for the empty graph, the second edge case is for the single node no edges, and the third edge case is for the cyclic graph. These are the 3 edge cases that we need to keep in mind, right? So now we are completely familiar with the approach as well as edge cases, right? Now we are completely familiar with the approach as well as the edge cases. As we are familiar with the edge cases and the approach, we are good to write the code. Let's start writing the code here. So first thing we have already discussed this one in the approach. So hash map is used to store already cloned nodes, right? So we don't have to clone the same nodes again. When we come to the next node, so suppose we might have the 2 or more nodes which previously, which could have already cloned, which would have all where basically we might have already cloned those nodes, right? It might contain those nodes. We have to avoid that one, right? We don't have to reclone that one again, right? So here we'll be making use of the hash map, which is basically used to store the already cloned nodes, right? So that is the reason we'll be going with the hash map. Basically I'll just go with private here map. So in this case I'll just go with node, node. This is fine. So here I'll just go with clones new hash map. This is fine. So let me do one thing. Let me cut this one and let me paste it over here. So let me format this one. This is fine. Give me a second. Now within the main, let's come to the main function here, clone graph. First step is, let's go with the edge case. When we have the empty graph, we don't have anything, we have to return null in this case. So I'll just give here, if node equals null, we need to return null. Means empty graph means we have to return null in that case, right? So this is fine. So the next condition here is, if we have already cloned particular this one node, then we have to return that from the map to avoid recloning, right? So that's the reason I said we'll be making use of the hash map. Let's write the same thing or articulate the same thing in the form of code here. Clones dot contains here, if I give key of node, so if the node is already cloned, then what we need to do, we have to avoid the recloning. So I'll just give here clones, we have to get the value we have to get the value of that particular node, right, which has been already cloned. So that is the reason I'll be making use of the get property, right? Get of node, get property, we are making use of it, hash map, that's an hash map property, right, to get the value. So this is fine. So the next thing here is, let's create the node. So here I'll just go with node, new node here, new node of here, node dot value. So this is fine. What we are doing here, we are cloning the current node and we are storing mapping, right? We are storing, or we also store the mapping here in this case, right? So that's what we are doing here. So in this line, in the line number 10, we are cloning the current node. Next, also we have to store mapping, right? So for the mapping, we have to store mapping. I'll just make use of the put property here. In this case, I'll just go with clones dot put of node comma new node. So it's not, there is no space here. This is fine. So the next step, we have to recursively, we have to recursively clone and connect the neighbors. So for all the this thing, for all the nodes, we have to check for all the nodes, right? So that one we will be doing recursively. So I'll just go with for node neighbor node dot neighbors here in this case. So I'll just give your new node dot neighbors. Let me copy the same thing here. I don't want to type this one again. This is fine. Oh, what happened here? Let me paste it over here. Let me make use of the add property here. Clone graph of neighbor. NAHH. This is fine. So final step, we have to return all. We have to return the new nodes, all the nodes, right? So we have to return all the nodes. We have to return the new nodes. So in this case, we have considered the variable new node here. Let me return the same thing. Simple, right? So this is it for the code. Let me format the code once and let me hit the run button. So here you can clearly see all the test cases are getting passed. So all the test cases are getting passed, means the code works absolutely correct in this case, right? So let me hit the submit button. Let's see whether this works for all the test cases or not. So here you can clearly see all the test cases are getting passed, means the code works absolutely correct on this, right? So let's quickly discuss the complexity of the code that we have read. So the approach that we went with here is DFS with hash map, nothing but the memoization, right? For the memoization part, we are making use of the hash map here, DFS with hash map, right? So what will be the overall time complexity here? So we are making use of the hash map, we know that, and also DFS. So here the overall time complexity would be big of n. Why it is big of n here? Because each node is being visited once here during during cloning, right? So we are cloning individual nodes. So each node is visited once during cloning. So it is overall time complexity would be big of n. N is nothing but number of nodes. We know this one, right? So what would be the space complexity here? Overall space complexity would be big of n as well. Why it is big of n here? We are making use of the recursion. Nothing but here in this case, we are going with the recursion, right? So we are making use of the recursive stack space, which can go up to big of n in the worst case, right? So if you remember, it will be like linked list like structure, right? So it would be big of n. So overall space complexity would be big of n as well. Also remember one thing, clones map stores one entry per node, right? Clones map stores one entry per node. Just keep this in mind. So overall space complexity would be big of n as well in this case. So the time complexity and the space complexity would be big of n, big of n. So the time complexity and the space complexity is big of n for the code that we have written. I hope the complexities are clear, and I hope whatever the code that we have written is completely clear as well, right? For now, this is it. Thanks.